Alright, time for another drawphysics.com, debatephysics.com also, but so few people willing to argue any parts of the actual argument. And the argument takes the shape of this idea that there is this kinetic energy formula that somehow, miraculously, creates all kinds of extra power if you're a light thing, and if you're a heavy thing, you're powerless. Kind of an argument. So every time you convert a heavy thing moving slowly into a light thing moving quickly, you create tons and tons of this kinetic energy. And every time you do the reverse, you destroy tons and tons of kinetic energy. And levers are also an example. So there's lots of physicists that talk about it. And so I found this video. And unfortunately, this guy hasn't made a video. Davenport, 1947. I guess he was born in 47. So he's an older guy, and I guess he's, past, as they say. He's been horribly destroyed, I guess. And so anyway, so it's not going to be a source of somebody to counter any of these counter arguments. But it's this, basic video on levers, and it really is just garbage. I mean, it really doesn't get to the actual function and the difference in these mechanisms, these simple machines as they call them. And they keep implying that they can create, free energy in a way, by not basically saying this idea of mechanical advantage doesn't mean that you're really going to gain more energy. You're just applying the energy in a way that's more suitable to the human. And that's it. Okay, it's easier for a human to apply the energy in one way versus another way. You can't punch something at 500 miles an hour. You just can't do it. So you have to do it in 50-mile-an-hour bursts. And that's And so as a practical matter, it's just a convenience. It doesn't actually multiply anything called energy. It doesn't make more energy. It doesn't make more force. It doesn't create more joules. It doesn't do any of that stuff. And they imply that it does, and it's clearly in the case of, putting energy in and then getting energy out in a lighter object. You put heavy energy in, you get lighter energy out, you're going to end up with this idea that somehow you made extra kinetic energy. And you could go all the way to the recoiling gun on one side, and I guess I might as well just go to drawing, and then we'll play some of this if I feel like it. We'll see. That could be better. It's close enough. So, the heavy object and then the light object. And if I go all the way to the extreme of, say, the recoil of a gun on one side and then the bullet on the other side. And clearly the recoiling gun only has 2 joules. The bullet has 2,000. It really is that extreme, 1,000 times more energy. And you really can't put the bullet in one side, even if you had an ideal lever and a mechanism that could do it. And you're still only going to get 2 joules out the other side. You can't fix that. It's part of the math. And it's part of the illogic of the whole equation. It's just wrong. The only thing that does anything in the universe is momentum. And the feature they don't talk about with levers is why do they do what they do. So the idea is you can have 2 styles of lever. Probably best to draw it here, I guess. So you can have the fulcrum at the bottom, or you can hang the lever, from the top. And these 2 things are different. One's a balance and one's not. And the difference is in what you could sort of understand if I draw the lever as a thick object. I could even go thicker. Okay, you can sort of, straight edge would be better probably. You could sort of understand that for the bottom one, the line that was going to be the perpendicular, the balanced line, now has a bunch of extra weight on this side. So this side is heavier. So the downside is automatically heavier. So if you're going to try to lift it, you can't just do the law of the lever and say, I'm just going to put, I'll put 1 pound out here, twice the distance, and have a 2 pound here. It ain't going to work because I still have more lever to overcome. So the weight of the lever is going to, in fact, keep it from balancing. It's going to stop it from balancing because it has to overcome that extra mass that was created by the fact that the lever is not in the balanced position. Now, if you start in the balanced position, you'll be okay. But as soon as you let one side get heavier, that side gets heavier and heavier. The more it goes down, the heavier it gets. So the harder it is to bring back up. So you can't use this as a balance. Now, if you hang it from the top, the exact opposite happens. So the line, okay, which would be here, I guess, yeah, well, I'll draw it the same color. You can really understand. This would be the perpendicular line for the, what it should be. And the fact is now the light side is going to, the side up, the upside is now going to get heavier. Now it's this big giant piece here. So it has this extra section that's added to this section. So now its mass went up. So it wants to go down because its mass is now up. And that's technically all that's really going to decide how the lever oscillates. So it's that change in the mass. So an ideal lever technically won't work as a balance because the ideal lever is massless. So if you have a massless ideal lever, it won't balance because there's nothing pulling the two balanced objects. The object, if I put a 1 mass here and I have a 2 mass here, okay, it won't balance because there's no differential. The two things are essentially in the same gravity. Technically this one's in more gravity, but it's so close to being equal, and so their pressures are exactly the same. So they won't change their position because there's nothing to balance, there's nothing to fix. And it's this extra mass here that's causing this side to go down, and it'll swing down. And when it swings down, what's it going to do? It's going to tip this side up. And when this side goes up, it's going to get heavier. And now this side will go down. And so what's oscillating is this little hunk here. It's oscillating from here to here, to here, to here, to here, to here. It's switching sides. And as it switches sides, it's going to cause the lever to keep oscillating. So the weight that's really oscillating is just that transfer of the lever's weight, not anything to do with the masses. If too heavy a mass here, 1.5, well then it'll swing down, it'll never swing back up, it'll never oscillate. So it has no hope of balancing. And so, that's the real mechanism. And physicists never tell you anything about that. They never even talk about that, ever. I haven't seen a single video where levers are discussed and they talk about the fact that the lever itself is really deciding how the lever behaves. And the masses are certainly important, but if they were equally spaced, if you obeyed the law of the lever, they're not going to make any effect. So when I had an oscillating balance, and I had 1 mass on one side and 4 mass on the other side, 4 times the distance difference, what was really oscillating was the mass of the little tiny bit of mass of the lever that was switching sides, oscillating back and forth. And that's really interesting. And so the other thing you can know is, I put this here, but this is less than free fall speed. None of this stuff is moving the speed it would move in gravity. So a great deal of the force is being put into the fulcrum, or the torque that this balance is going to feel. So it's either going to be a weight on the fulcrum, or it's going to be a torque on that string that will eventually go into the ground. And that's where a good deal of the energy is actually going, because the objects are in gravity much longer. So in free fall, the whole thing would happen very fast, but nothing's moving the free fall speed. So it's collecting the 9.8 more of it because it's taking its time to do this balancing. The weight's moving very slowly, and that's what's allowing for the fact that you only have twice the height here. Okay, will equal twice the velocity. Now it's a given, you can't really avoid this moving twice as far as this. This out here moving twice as fast as this object. You can't change that, but that's how it's doing it. That's how the conversion's taking place. And you're taking something in free fall that would take 4 times the distance, and you're cutting it down to just twice the distance, because you're going to reach twice the velocity by only traveling twice the distance. All right, so this is all stuff the usual conversation on levers just totally overlooks. And again, the kinetic energy theory has this idea that somehow if I put a certain force in on one side with a heavy object, I'm not going to get the same momentum out of the other side, because that would be free kinetic energy. So they're going to claim that I can't put the gun recoil in this side and get the bullet out the other side, because I can't turn the 2 joules of the gun recoil into the 2,000 joules of the bullet. So somehow light things are harder to push is the basic element of their theory, and it's nonsense. As the ballistic pendulum proves, as the we can go back to the 5 tons, 5 mass, okay, going 10 velocity. I add 5 mass to it, pour water into it, whatever. I add 5 mass, and so now it's a 10 mass. And in every experiment, it ends up going 1/2 the velocity. So it's a 10 velocity, it's going to go 5. And that is going to be perfectly conservative of the momentum, and it will completely destroy kinetic energy. Yeah, I didn't like that. Yeah, it's getting glitchy. Alright, I guess I need a reboot. Alright, I should be back. Probably. Alright, we'll assume we are. Anyway, okay, so we'll play some of this video. Just unfortunate, like I said, this isn't going to be a participant, so it's kind of a pointless exercise in some respects, but whatever. So somewhere around here he starts getting to the subject.
Of the force that you put into it. Rather than increase the force, it allows you to change the direction of the force.
So he's talking if you just took this by, if you did equal distances. So, if you did unequal distances, of course, it's not going to be just multiplying it by 1. And again, it doesn't really change anything. The net force is the same. So this is where force gets messed up, because they're measuring force in this idea of a foot-pound per meter. That's this Newton per meters thing. So they're measuring it based on distances rather than based on what, in all these cases, the more relevant component, which is the time you're applying the force. So it's really about how much time a force is active that will decide how much work it can do. And you can talk about a force, big F, the force that's net, the total amount of force you applied, versus talking about the force in terms of something like 9.8 meters per second, where you're talking about a force that's going to happen over a period of time in increments. Okay. And it's always going to be a net amount based on time. So I mean, all these things are events, and the events have a beginning and an ending. So you can say, yes, no matter what we're talking about, there's going to be a total force. So if I drop something on the lever, there's a total force of its impact, and that's just going to be transferred to the other side of the lever as a total force. And the whole point is you're changing something that, say, is happening at 9.8 meters per second to something happening at 4.9 meters per second. All you're doing is really just changing how you're applying the force, how much time it takes. Okay, and by increasing the time, you can increase or decrease the amount of force you have to apply per second over that time to equal the same net force. So applying 5 pounds for 2 seconds is the same as 10 pounds per 1 second. And, it's all momentum. Momentum works. Kinetic energy fails. I mean, it's just, it's really amazing that there isn't enough intelligence okay, to concede the point that you're all just too stupid.
So if you want to design a machine to make work easier by allowing you to change the direction of a force.
Right, so the direction, it's basically saying, yes, you can do that fundamentally, essentially for free. Okay, you can change its direction. And that's also an interesting fact, is that you're afforded that opportunity. Okay, continuing.
This is the machine. A good example would be the pulley at the top of a flagpole. If you put 10 newtons into pulling the rope down,
you're only going to be able to put 10 newtons on the other side, and it just depends on, again, 5 newtons per meter over a longer period of time is the same difference.
You can lift the same force as a flag on the other side, but the flag goes up the pole while the force that you're pulling on the rope with goes down. The pulley at the top simply changes the direction of that force.
And probably steals some of the energy, so you do have to concede it steals something. And it depends again on how much time, how long the event's taking place will decide how much time the fulcrum will steal.
So it does just exactly what it's designed to do. Well, let's take this to the next step. What happens if we change the...
So we know it doesn't do exactly these things. None of these things do exactly work in the exact real world. So the fact is that the lever, the weight of the lever is relevant in all cases, because you have to give it momentum. So it has to use some of the energy you're trying to transfer from one side to the other and convert from, a 10-pound force over 1 second to a 5-pound force over 2 seconds.
The length of the input side with respect to the output side. Well, here's what happens. Here's our first-class lever again.
So this would never work just because the lever itself is now imbalanced. So it's going to sort of cheat the experiment. If you've lifted the lever up, then you've lifted this mass, up. This greater mass on this one side. So this is obviously going to be more work you have to put in just to even lift the lever to wedge it under something. You've done extra work, and you'll get that back when you push the lever down, because you're going to go in the same direction that gravity wants to push it anyway.
The input side here is 2 meters long. The output side, measured from the fulcrum to where the weight is that you're going to be lifting, is 1 meter.
So it doesn't really matter, frankly. It's moving the fulcrum obviously is just giving you, just makes it easier for you to say, well, this is 1 distance and this is 10 distances. So just giving you an obvious visual of what you're doing, but the visual isn't necessary, especially in the ideal case, which he's talking about. It wouldn't make any difference. You're just really talking about making the distinction. I mean, this is really just talking about, well, what's convenient for wedging under a rock? Well, yeah, you need the fulcrum close, because you'd have to have a really long arm on the other side. This arm would have to be really long if you left too much on this side of the fulcrum. But I mean, if you're going to talk in ideal terms, you should have the same weight of lever on both sides.
The 2 sides are different lengths. Input side here 2 meters, output side 1 meter. If I apply a force of 100 newtons to the input side of this lever, then I might ask, how much force can I get out on the output side?
Right, and you can't change how much force you're going to get, so that's the big kind of a lie. All right, you can put 100 pounds on this side, so talk in terms of weight or momentums, and you can, move 50 pounds twice the distance. That's the real truth. So, you can move it twice the distance against the gravity. But that's all. You're not going to be able to make more energy. You can't increase the force.
And I can figure that out by figuring out the mechanical advantage. And specifically what I'm going to do here is I'm going to figure out something called the ideal mechanical advantage.
So that's even more ridiculous, just because obviously none of these real world circumstances have anything to do with that ideal. So, why not deal with the actual reality, which is, if you are going to lift something and you're going to have a fulcrum underneath, then you're lifting more, because the fulcrum, it means it's going to push more weight onto the other side. Now in this case, it's going to be a lot less weight than the total weight of your lever, so it's not going to hurt you much. But it depends on how heavy your lever is. So if the lever was a 2x4 and you were trying to manipulate objects that weighed, an ounce, it would totally fail because the change in the mass of the lever would be greater than the change you're trying to invoke.
Why is it ideal mechanical advantage and not just mechanical advantage? Well, the ideal mechanical advantage, or IMA, ideal mechanical advantage, means that we're not taking into account the friction involved in this machine.
So you're not taking into account the fact that nothing's going to move at a free fall speed. Nothing's going to be moving at its ideal speed against gravity. That is the velocity that will be the most efficient. And the fact is there's going to be a lot of pressure on the fulcrum and a lot of force will go in a lot of places. But yes, you will gain the simple mechanical advantage of you can cut a job and you can make the job twice as long and do half the pressure. You can punch it 5 times and have those 5 punches converted into one big punch, with 5 times the impact.
It is a perfect machine, which really doesn't exist. It's an ideal machine with no friction.
And again, the ideal wouldn't work. So again, without the change for a balance anyway, you can't make a balance out of an ideal lever. You need the lever to have mass for the balance to work.
So, I can calculate the mechanical advantage, the ideal mechanical advantage for this machine. I do it like this. I compare the two sides of the machine. We have an input side here, and we have an output side. The ideal mechanical advantage is...
So most of this video is this kind of, this is supposed to be, he's a high school teacher. This seems a little below high school level kind of rhetoric, that you have to explain that you're pushing on one side and that you're lifting on the other side. Yeah, I think everybody could figure that out.
Simply the ratio between the input side and the output side. The ideal mechanical advantage then is the input side, 2 meters, divided by the output side, 1 meter. And what this means is, when I find the answer is ideal mechanical advantage is equal to 2. This ideal mechanical advantage would be exactly the opposite of an advantage if you turned it around the other way around. So if you're applying your force on the other side, then it wouldn't be human fun anymore because now you have to apply the energy twice as fast to the other side, and you can't do it. It's going to be more work for you because you can't lift 100 pounds. So we're just back to how it's just which way you use the damn thing decides whether it's an advantage or a disadvantage. So you use it the opposite way, it's a huge disadvantage, but you can't change the total energy. You're not changing how much energy it takes, you're changing how you apply the energy, the force. It's the same force, you're just changing how it's applied. The same net force. Lever will multiply any force that I put into it on the input side by a factor of 2.
So it's not going to multiply a force. It's not going to happen. The force will not be multiplied. You can multiply the rate. So if it's a force at a rate, you can multiply it. Okay, so I can do 2 seconds of the 4.9 or 1 second of the 9.8. But I can't change the net force.
Because its ideal mechanical advantage is 2. The ratio between the input side and the output side is 2. By the way, the input side is also referred to as the effort side. And the output side is referred to as the resistance side. So I'm moving a resistance force with an effort.
Yeah, whatever. This is all just for whose reference. I mean, that's kind of narrowing a simple tool and saying, oh, we're only going to use it for one purpose. It has multiple purposes.
Force. I put an effort force in, I can move a resistance force, and in this case, you can see here that the resistance force I can move is 200 newtons. The input force, the effort force, is multiplied by this machine by a factor of 2.
So it isn't. All right. All you're doing is saying I'm going to be applying the force over twice the distance, twice as long, essentially, in a sense. Okay. There's force being applied over twice the distance over on this side that you're applying the force on the other side. So obviously it's not the same. And then you could just say by the net movement, you're moving this twice as much, moving it against gravity, let's just say, for example, and you're lifting this half as much. So you're not going to be you're not taking 100 pounds lifted on one side. I lifted 100 pounds, 2 feet. Well, you're only lifting the 200 pounds on the other side 1 foot. So you can understand it's not the same thing. You didn't convert. There's not an equal conversion. You didn't lift the 200 pounds to the same height. So it's obviously not the same force. I mean, it's the same force, and it's just you have to understand that you're not doing the same motion to the object. You can't do this direct conversion and say, I made a 200 mass move the same distance I made the 100 mass move. You didn't do that. You gave it half the velocity. I mean, it's the bottom line. You put twice the velocity in, you only got half the velocity out.
Which allows me, in this case, to lift 2 times as much as I put into it.
So you're not really doing that because you're not lifting it as high. So it's not the same. It's not a fair comparison. It's not a fair way to state it. You haven't changed the net amount of force at all. You're just changing over how much time, you have to apply a force.
That's a good introduction to how this works. So let's go ahead now and work on a few very simple lever problems to get used to using this idea of ideal mechanics.
So they just waste a bunch of time doing the same thing over and over again, and try to trick you by doing 2.5 into 4.7. I mean, why would you bother doing that?
Advantage. All right, let's go ahead and solve a problem. And problem 1 here is obviously a first-class lever, just like we've been looking at. And the first thing to do here when you look at a lever is to identify the input side and the output side. Well, the input side is where you put a force or work into the machine. So over here where we...
So there's just no way of getting whatever this, again, this is saying 200 newtons is that's just a weight technically. And you can't just put a weight in, and get motion out.
We have a force of effort of 200 newtons. That's going to be the input side, and I'll label that with an I. And over here where we have an object that's being lifted, then I'm going to label that O for output. So we have an input side and an output side. The first step here is...
And again, if you're lifting it, see, obviously the lever is not going to be balanced especially if you're not applying the force to balance it. So it's going to be, this is going to be down, which means this side of the lever is going to be heavier. It's all something that's got to be appreciated.
To go ahead and figure out what the ideal mechanical advantage of this machine is. Ideal mechanical advantage, if you recall, is equal to the input side divided by the output side.
So this is just the law of the lever, and again, you're not converting, you're not creating any extra force. You're just applying it over a different amount. You're applying it with a different velocity. I mean, it's the only way to say it. The velocities are going to be different. You're going to put in a low velocity, you're going to get a high velocity out, or vice versa. Alright, so I don't know, skip ahead a little bit. It's the same crap over and over.
Sides. And so what we're saying here is that whatever force we put into this machine is going to be multiplied by a factor of 2.7, and that would give us the weight that we can lift on the other side.
And you'll lift it 2.7 times less high. So, I mean, clearly you're not applying the same net force because you're not lifting it as high. You're moving it 2.7 times less distance. So obviously it's not the same, it's not comparable. You're not getting the same result. You're not forcing it to go to the finish line. You're saying, how much gas does it take to win the race? Well, you don't put enough gas in to win the race. You didn't put enough in to get to the finish line. So it's not a fair comparison. Alright, I think that's all that needs to be said. I mean, there's probably some little bit here where he says again about increasing the amount of energy, but I won't nitpick. I mean, I won't go through it just to find that little bit where he says rhetoric that just is wrong. You can't increase the energy. You can't increase the force. You can just change how the force is applied. The net force. Alright, the total force will not change. Alright. it's probably enough of a video. I will declare it so anyway. But yeah, it's always, it's a subject that has to be gotten back to just because it is ripe, okay, for debate in the kinetic energy versus momentum argument. Because frankly, used correctly, levers are conservative of momentum, and they will demonstrate that speeding bullets don't have 1,000 times more energy than recoiling guns. All right, anyway, till the next time and such.